Hello everyone. In this example problem, we will be discussing how to carry out a fatigue analysis, specifically when dealing with a combined loading problem. Now, I would suggest watching this entire problem in two parts because it's really long and there's a lot of information, a lot of moving parts, and it would make more sense for you to understand the first half of it where we deal with just the loads and um, separating out the stresses and then going on to conduct the fatigue analysis. Okay, so what I'm going to do is read the problem statement, see what they're asking us for, and then I'm going to talk about the procedure a little bit, which is in a separate document that is uploaded to Canvas, and then we'll start applying this to our problem. So we have a cantilevered bar in the figure below. It's made from 3140 normalized steel, so we know the material properties, and it is fine ground, so we know the surface finish. It is statically loaded with two loads, two non-zero loads in the y and the x direction. So you have a load in the y direction that causes a torque and a bending. You have a force in the x direction that causes an axial load and a bending, and the z force is 0. Analyze the stress situation in the small diameter at the shoulder at A by obtaining the following information. So we don't need to solve stresses at different points to figure out what's the critical point. We only need to carry out the analysis at the shoulder here. So there's a fillet, there's going to be some nominal stress due to the 1-inch diameter, and then we'll have to figure out what the safety factor is with respect to infinite life. So again, determine the precise location of the critical stress element at the cross section at A. This is something you've already done, where you just figure out what the bending moments are, and then you know exactly what direction from what some axis this critical stress element is located. Then you have to sketch the critical stress element and determine the magnitudes and directions for all the stresses acting on it. So it's basically your sigma and tau equations as a function of the moment and the torque respectively. And for the critical stress element, determine the principal stresses and the maximum shear, which is basically the Mohr circle. So all the stuff we've done in terms of static loading, except for the failure theories, is something you should be comfortable with, and it should be easy for you to go through problems, parts A to C of this problem. So I've already done this. The solution is written out. I'll post that alongside my notes. All we need to conduct the fatigue analysis are the nominal stresses from part B. So the magnitudes and directions of the axial, the bending, and the torsional stress. And finally, build upon your results from parts A to C to determine the minimum factor of safety for fatigue based on infinite life, using the modified Goodman's criterion. So that's basically the simple Goodman's equation, which is your mean stress over your ultimate strength plus your alternating stress divided by your endurance limit is equal to 1 over the safety factor. Now, if you were to solve for that safety factor, given the stress conditions and the material properties, if the life is not infinite and the safety factor is less than 1, then you need to estimate the number of cycles. And the forces that are applied are repeated loads and perform a fatigue analysis using a 99% reliability. So let's look at the document that's posted on Canvas. So if you go under week 3, fatigue, you have something called the recommended fatigue procedure. Now, this document lays out the procedure recommended to follow when carrying out your fatigue analysis. So Juvenile has one approach, and a textbook that we used earlier, Shigley, we thought that that lays out this fatigue process a little more extensively, and it's able for you to understand, you're able to understand exactly what's happening. So we feel like this is a better analysis in terms of how numbers move around and where do these numbers come from. So it is so we would highly recommend that you learn this process rather than the one that's laid out in the juvenile textbook to carry out your analysis on combined loading problems. So basically in this PDF, the first part talks about just calculating the endurance limit. So Sn prime is just zero point 0.5 times SU, right? But that's only if your ultimate tensile strength is less than or equal to 1,400. If it's greater than that, then just flat out use 700 megapascals. Then what they call the Marin factors or the correction factors. So you have to, depending on the type of loading you have, you just have 1.85 and 0.58. Now this is a little different in the juvenile textbook, so we suggest you pick out all the values you need for the Marin factors or the correction factors for your endurance limit from this document here. The gradient factor depends on the size. 1 and zero point 0.9 is similar from juvenile. This is just an equation that says what happens when you have really large values. So we'll try to stay away from using these values, especially in the exams and quizzes. But if they were to show up, you can use this equation where you say that the gradient factor is equal to 1.5 d to some exponent, and you should be fine. And then the surface factor, because we picked it up from a plot, we'll use the exact same plot that you have in your textbook, which is figure, I believe, 8.13. So this is what you've already seen in juvenile. So I think this is juvenile 8.13. And so that's pretty straightforward. The temperature factor, again, if it's less than 840 degrees Fahrenheit, it's going to be 1, or in Celsius, less than 450 degrees Celsius. That's kind of where we will do all of our analysis for most of our conditions. So it'll be 1 for the most part. If not, then you can use the equation that's mentioned. And the reliability factor, depending on the percentage you're looking at, you will be dealing with a different reliability factor. Now, these values are also in your normal distribution table. So again, if it's related to the normal distribution table. So that's where you get these values from. 50% is 1, and it drops from there. Okay, so this is basically just laying out how to calculate the endurance limit, and it's similar to what you've done in juvenile, except there are some minor tweaks. And I would suggest using these and just to maintain consistency. All right, so this is just the endurance strength, and then that's the equation where you multiply the factors with Sn. There should also be a Ct here, so I'll add that. I'll revise that copy. Okay. Then once we know what the endurance limit is, we can figure out what the stress concentration is as well. So like in this problem, we have a shoulder, right? So there we have plots from chapter 4, which talk about the stress concentration factor in static loading. And then we're introduced to something called the knot sensitivity Q. And Q again I think this is figure 8.24 in juvenile. So this is also from your juvenile textbook. So it's something you can pick out. We'll talk about how to pick out values from here if you're not comfortable with it yet. And then depending on the type of loading you have. So if you have simple loading, means you have either pure torsion or pure bending or just pure axial, then you can just use these equations right here for mean and alternating stress, and then directly plug it into the Goodman's equation once you're done. Now this is if you have bending stress. If you have, let's say, shear, right? If you have pure shear, then I remember from the previous text example problem, we had tau mean over SUS plus tau alternating over SN is equal to 1 over N. So here you have to use the shear yield strength, and Sn here would have your CL equal to 0.58 is basically what it's saying. So you'll have to adjust that accordingly. Okay, so now the combined loading problem. What's going to be different? When we combine the stresses, right? So we have to calculate the nominal bending stress, nominal axial stress, and nominal torsional stress, both alternating and mean components. So if you have all three of them, you're going to end up with 6 stresses. Once you have 6 nominal stresses in the mean and with mean and alternating components, you need to multiply them by their stress concentration factor Kf. And now Kf is a function of both Q and Kt. Once you have Kf, you multiply this. So this is basically going to be your max axial bending stress. Sorry, max alternating bending stress. This is going to be your maximum axial alternating stress, and it's going to be your maximum torsional alternating stress. So you have to keep them separate throughout. And then you multiply them in this equation. You can multiply them beforehand, so the computation is easier if you're doing it in hand, but make sure you're keeping track of your variables. So this is the way to combine them. It has the same structure as the distortion energy theory equations. Now, juvenile says not to use it, but we suggest you do. And for sigma mean, it's a very similar equation. It's actually almost the same, except for one thing, which is the 0.85. So the reason 0.85 shows up in the alternating and not the mean is you can think of the mean stress as a static stress that's always being imposed, and then the alternating as fluctuations. and it is the fluctuations in an axial load that make it detrimental in fatigue loading. So that is why the 0.85 only shows up in the alternating stress than in the mean stress. And then finally, once you combine them, you can use the equation again for the Goodmans. But now because you've combined them, there are some things that you're restricted to when you're calculating the other terms. So SUT is always SUT. Even if you have just pure torsion, but you decide to use either of these equations, then you need to make sure that you always use SUT. And if you use sigma, and for SN, you always use the bending values. So I'll explain what this means in the problem as well. But remember, if you're calculating the endurance limit, you only take it with respect to bending. And that's what it says here. The load factor returns to unity. And for unity, it is basically bending. Now, in order to use the modified Goodman's equation, we need to ensure that the material does not yield. So there's a quick check that you would need to do before you go ahead and use the Goodman's equation. So I would suggest that you would do, this would be C and this would be D. So check for yielding is basically adding these two stresses and then dividing them by the safety factor that you're interested in. Again, this is a very conservative value. So if you get something like 0.9, I would say you can go ahead and use the equation because this is actually a very, very conservative estimate of yielding. There are other equations in the juvenile or Shigley textbook that make it more apparent, but this is kind of, if this is greater than 1, if this n value here is greater than 1, then for sure there's no yielding. So just remember that. And we would suggest you always check for yielding. Now, if it's an example problem and we give you a really long problem like this, we probably expect you to get to solving for the safety factor. So we won't give you something that yields, but there's no harm in checking for yielding. All right. Now, what happens if Sn or your safety factor in the Goodman's equation here happens to be less than 1? That means that if I look at my Sn curve, that means your material doesn't truly achieve 10 to the 6 cycles. It's going to fracture somewhere in this region here. So in order to find out what that value is, we need to figure out what that strength is. So the way to do that is solve for the denominator of the alternating term. Because like I said a couple of examples ago, that term kind of tells you the stress that you can achieve in the alternating stress that you can achieve with respect to a given safety factor if your value is less than, or if your strength truly is greater than the endurance limit. So what I would suggest is if you end up with a safety factor less than 1, you can go ahead and substitute, let's say your safety factor equal to 1. Let's just set this equal to 1, depending on what safety factor you're dealing with. And at least if this drop less than 1, then you need to make sure that it's less than 1. And set that equal to 1, solve for this value here, and then which is called the equivalent fully reversed bending stress. And then you plug that value in the log equation from Appendix I and solve for the life. And that basically tells you, you know that it's going to be less than 10 to the 6 cycle, but what is that value? What is that finite life? And this is basically the procedure we will follow to solve this problem. All right. So let's go to this problem. And from parts A to C, all we need to know are the nominal stresses, right? Because there are no principal stresses that show up in any of the equations when performing a fatigue analysis. So again, I will post the solutions to how I came to these values, but sigma nominal in bending. So let's go sigma bending nominal is, in this case, it would be sigma bending x, or sigma x nominal, is 46.1 KSI. Then sigma axial nominal is 0.382 KSI. And tau torsion nominal is equal to 15.3 KSI. So that's basically the nominal stresses due to torsion. Now torsion is caused due to Fy. Bending is a combination of both Fy and Fx. Fy and Fx. Torsion is simply due to Fy, and sigma axial is simply due to Fx. And these are the nominal values that you have. Now this is just static loading. We're not looking at any sinusoidal waves or whatever. That's something we're going to do next. This is just the nominal values. And again, of course, we're ignoring shear stress. Because it has this significantly high L over D ratio. All right, so you have this wrench sort of setup, and you're going to twist it when you have some load also in the axial direction, and you're trying to analyze the stress here and its failure. And because up here it says these are repeated loads, so that means Fx and Fy are on and off. Now there's a difference between repeated and reversible. Repeated means it's on and then it's off. So it's going to go to a maximum value and then back down to zero. Reversible means it's going to go to some positive value and then it's going to go to the exactly same negative value. So it's going to be alternating about the zero, and repeated means it's going to be alternating between a max, fluctuating between a max and a zero with some non-zero mean value. Okay, so now the first step is to draw the profiles. So let's look at first sigma bending, or the bending stress. So let's draw it as a function of time. And this is basically how I would suggest starting any fatigue problem, is to draw the profile. So this is your sigma bending as a function of time, right? And it said it's repeated. So it starts off at zero, some maximum value, and then it's back to zero. And we'll always assume that all loads are applied in a sinusoidal fashion, where this value is going to be the maximum value applied, which is your sigma bending nominal, right? And this is zero. Similarly, with the axial load, you have, again, it's repeated, right? So the bending here says that, okay, at any point on the shaft is going to be either fully, let's say, for example, we're looking at some point here on the shaft. So it's going to be fully in tension and then nothing, fully in tension and nothing. And if I look at exactly on the opposite direction, fully in compression and nothing, fully in compression and nothing. But the reason I chose tension is because if you look at the axial load, it's pointing outwards, so it's stretching the shaft out. That means the two tensile normal stresses are going to build upon or sum together to give you a larger positive stress. So axial is also going to be, right, either fully in tension or not in tension because it's being pulled out. So this is your sigma axial nominal as a function of time, and then torsion or shear due to torsion is going to look the exact same. So it's going to twist your beam, and then it's not going to twist your beam. It's going to twist your beam and then not twist your beam again. And this value again is going to be tau nominal. Okay, so what can we get from these profiles? What we can get is the maximum and the minimum stresses. And based off that, we can figure out what the mean and the alternating components are. Now, some of you can just look at it and tell what the max and what the mean and the alternating are. But sometimes if it was offset from zero, then it's safer to write down equations to do this. So what are the equations? So sigma mean is going to be your maximum stress. Now this is for all three cases. So it's going to be a maximum stress plus a minimum stress divided by 2, and your alternating stress is going to be your maximum stress minus your minimum stress divided by 2. So we'll have to carry that out for bending, alternating, axial, and torsion. So let's look at bending first. So we have sigma bending mean is equal to sigma max, which is your sigma b nominal, your sigma min, which is 0, divided by 2. So your mean bending stress is equal to sigma b nominal divided by 2. And the same goes with the axial stress, right? Because they have the same profile. Your axial stress is also going to be, axial mean stress is going to be sigma axial nominal over 2, and the same profile with your shear. So we have tau torsion mean is equal to tau torsion nominal divided by 2. And then we can solve for these values, right? Because we already know what sigma b nominal, axial, and torsion are. And that's our 46.1, 0.382, and 15.3. So if I were to write that out, again, this is just the nominal mean stress and the nominal axial stress. And those values are 0. Sorry, no, 23.05 KSI, 0.191 KSI, and 7.65 KSI. And now let's look at the alternating components. So we have sigma max, right? I'll just do it for bending because they all have the same profile. The alternating component will be your sigma max, which is your sigma b nominal minus 0 over 2. So it's going to be sigma bending axial will be again sigma b nominal over 2, which is equal to 23.05 KSI. Now the reason the alternating and the mean components are the same is because it's fluctuating from 0 to a maximum value, where your mean value is exactly in between the two, right? So this is going to be your sigma mean, and this distance here, which is your alternating stress, is also going to be half the height, right? Half the amplitude. So that's why they're both equal in this case. Now, if it was offset, let's say you had a situation where your stress looks something like this, right? Then your sigma mean is going to be up here, mean is up here, but you're alternating. If this was short enough, then this would probably be smaller than your mean stress. So I would stick to the equations. So it's not very apparent when it's not 0. So make sure that you understand that it's not always equal. Okay. So in this case, all of them are going to be equal. So we can just straight away say that sigma axial alternating is also equal to 0.191 KSI, and tau torsion mean is equal to 7.65 KSI. Okay, now that we have the mean and alternating components of our stresses, we need to introduce the stress concentration factors. Because without the stress concentration factors, we won't truly understand what the stresses look like at that shoulder. So let's look at stress concentration. So this is the first step. First step is mean and alternating stresses. Okay. Now we'll look at stress concentration factors. Specifically, we're solving for KF because we're in fatigue loading. Okay, so let me write down the equation for KF first. So KF for any type of loading is going to be 1 plus KT minus 1 times the knot sensitivity. So we need to solve a KF for bending. We need to solve for a KF in the axial and a KF for torsion. So again, for that, we need to know what KT is. So first we need to find a KT axial, KT bending, and KT torsion. So we need KT bending, we need KT axial, and KT torsion. So now this is chapter 4 of your textbook. And because we have a step shaft, this is going to be 4.35, 4.35 A, B, and C. So what do we need to know for this? We need to know the R over D ratio and the D over D ratio. So let's calculate those. So we need R over D, and R here is 1 over 8 inches, so 0.125 inches, and the small diameter is 1 inch. So we have R over D as 0.125 over 1, so that's 0.125, and then D over D is 1.5 over 1, which is 1.5. So basically, we're looking at 0.125, so I'm just going to draw a line that goes across. So we have, change the size, this. So we're looking at 0.125. Looking a little closer, 0.125. All right. Now let's look at D over D for 1.5. Now on the first plot, so this is KT for bending, right? Because you have moment arrows pointing downwards, that means bending. We're going to look at 1.5. So 1.5 is the third line from the top. That's going to be some value here. So 1, 2, 3. So that's about close to 1.6, 1.5, 9. I'll just say 1.6. So 1.6. Okay. Then let's go down and look at axial loading. So we have again 0.125, and this is the second line. So we have something a little lower than 1.8. So I'm going to say 1.75. 1.75. And then finally, in torsion, it's in between these two lines. I'm just going to say, okay, it's in between 2 and 1.2. I'm just going to choose, wait, I think the line's offset. Yeah, the line's offset a little bit. I'm just going to move this line. Oops. Okay. This isn't working that well. Okay, so it's moved a little bit. And we'll just say it's about 1.3. At least in my figure here, I have it as 1.39. So we'll just use 1.39 for now. I know it doesn't seem like it, but that's how I calculate my values. So let's just take it as 1.39. 1.39, 1.35, anything above 1.3 to 1.4 is fair game. So that's okay. So 1.39, 1.75, and 1.6. Okay. So this is a very tedious process. It might be really slow right now, but it's important that you understand, that you have three different stress concentration factors because you have three different types of loadings. So 1.75, and I have 1.39. Again, this is figure 4.35, A, B, and C. Okay, so now that we have KTs, we need to find Qs. All right, so we need a Q in axial, Let's do it in a different color. So we need Q, bending, Q, axial, and Q and torsion. So let's look at what we need to solve for Q. So Q is the notch sensitivity, Q is figure 8.24. So for that, we need to know the notch radius and we need to know the strength of our steel, either its hardness or its ultimate tensile strength. So now we need to go back, we need to take a step back and figure out what that value is. So the material we're dealing with here is 3140 normalized steel. So in your textbook, juvenile again, Appendix C4A, you have 3140 normalized steel, and we need the ultimate tensile strength. And because we're dealing with KSI units or the British Imperial System for this entire problem, we're going to take KSI, which is 129.3. So I'm going to quickly mention that down here. SU is equal to 129.3 KSI. So I'm going to go back down and solve for Q. And the notch radius we said was 0.125. So I'm going to draw a line again across 0.125. 0.125 is somewhere here. Okay. And first we'll look at bending. So it says to use these values with bending and axial loads. That means we're going to have the same notch sensitivity in bending and axial loads. So that's one less value we have to find. So it's going to be somewhere here. And we have 129, which is in between these two lines right here, because this is in KSI. So it's somewhere here in between the two, exactly in between. So this is here, which is 0.85. So that's for bending and axial loads. And for torsion, it's going to shift up by one line. So it's going to be somewhere down here. So we're looking at something really close to 0.9. So I'll say 0.91. Okay. So based on the strength of the material and the notch radius, we have 0.85, 0.85 because they're the same, and 0.91. Excellent. Now that we have the stress concentration factors, your static loading, and the notch sensitivity, we can go ahead and solve for the stress concentration factor in fatigue. So Kf bending is equal to 1 plus, zoom out a little bit. So Kt is 1.6, so minus 1 times 0.85, and we have 1.525. Kf axial is 1 plus 1.75 minus 1 times 0.85, and that is 1.656. And Kf in torsion is 1 plus 1.39 times 0.91, which is 1.355. So these are the stress concentration factors that we will use to calculate the actual stress, planar stress in bending, axial, and torsion. Okay. So now that we have values, let's look at the stress with stress concentration factors. Oops. I'm already tired. Stress concentration factors. Okay. So now we have a mean and an alternating um, type of stress. So I'm going to draw a line down the middle, do all my mean stresses here, and do all my alternating stresses here. So again, I'm going to start off with bending. So sigma, what I call is sigma bending mean. Now I use sigma bending mean here and sigma bending mean here, but these are two different values. So what I'm just going to call it, I'm just going to call it sigma BM. Again, it's difficult when you have so many variables. That's why in what happens in the document here is they just write it out in the equation. They don't. So what I'm doing right now is multiplying this beforehand. So I'm dealing with less numbers in this under the square root, but you can keep them separately and just combine all of them in your final equation. So you don't need to create so many variables if you don't want to. Okay, this is going to be KF bending times your sigma bending. Oh, this is going to be a nightmare. Okay, this is basically KF times sigma nominal mean, and this is going to be KF times sigma nominal alternating. And I'm just going to write down the values. Again, these are the values from before. So sigma bending mean, where did I write this down? 23.05. Okay, 35.15 KSI. Sigma axial mean is 0.3163 KSI. Now I know this is the axial value is a lot smaller than the bending value, but I'm just keep using it in this analysis so you understand how to, keep these values separate and how to calculate different factors for each of them. Because I want to use that 0.85 in the equation at the end to show you that, you know, not to forget that in case the axial loads are actually high enough. But if you're running out of time in the exam and you think it's small enough, you can just say, okay, small enough to ignore and then move on. And finally, tau due to torsion mean is 10.36 KSI. Now, because they have the same stress concentration factors, again, stress concentration factor is independent of whether you're dealing with the mean or the alternating stress. It only depends on the type of loading. So, and because sigma nominal is the same for mean and alternating, in this case, sigma bending A is equal to 35.15 KSI. Sigma axial alternating is 0.3163 KSI, and tau torsion alternating is also 10.36 KSI. So now that we have the actual stresses, mean and alternating stresses at the shoulder, we can go ahead and combine all the stresses now. So 4, I believe. Yeah. So combine mean and or alternating stresses using the von Mises equation. Or von Mises stress. Okay, so let's write out the equation first. Again, this is from the document over there. So you can call it sigma E equivalent. Let's do mean first. Mean, or you can call it sigma mean prime. The prime just comes from the distortion energy equation. which denotes a prime for von Mises. The Shigley textbook uses E. You could use either, but be consistent. So that is, okay, so we have your sigma bending mean plus your sigma alternating axial mean square plus 3 times your torsional shear mean square and the square root of that. So sigma E m or sigma m, I'll just stick with sigma m prime. If you substitute these values in there, you have, okay, so you have 35.15 plus 0.3163 square plus 3 times. Again, a lot of times students put the 3 inside the square as well. You shouldn't. The 3 actually sits outside the square. So you only square the tau value. So that's 10.36 square and the square root. So just sum of squares and take the square root. Sigma m prime or sigma em is 39.75 KSI. Okay, and then similarly, the alternating stress, we have sigma EA or sigma A prime, and it's basically the same equation except for where we have the axial load, we have an extra factor, so we have sigma BM plus, sorry, A this time, it's alternating. So alternating plus sigma axial alternating divided by 0.85 square. Let me see if I have this down right. Plus 3 tau torsion alternating square. And we take the square root. So sigma A prime is 35.15 plus 0.3163 over 0.85. So we should expect a smaller value than sigma m prime overall. And then this will be the same thing, 10.36 square root. So we end up with sigma A prime equal to a slightly larger value. Sorry, the 0.85 is in the denominator, so that blows up the numerator, which is your sigma A prime. And that is 39.8 KSI. Okay, so this is basically your combined stresses. And now would be a good time to take a break. Just absorb all the material that I just covered. Take a 30-minute break, take a day's break, whatever works best for you, and understand the procedure here. So, quick recap. Figure out what your stresses are, right? Depending on the force, using all the tools you've learned up until now in the class. Draw the profile out, sort out your means and the alternating stresses, figure out what your stress concentration factors are. Then you can individually multiply them right now to figure out what the actual stress is, or you can combine them in the equation here and solve for your combined mean and alternating stresses. And this is basically the stress state under fatigue that your material is undergoing, at least in this case, in the critical section.